Welcome back, and now we continue with the discussion of the semi group coming from the heat equation, namely this W T F is K T star F. Okay, so now we will prove the strong continuity. So, what you have to show? What you have to show is W T F, okay, L P tends to 0 as t tends to 0 plus for all f in L P. So, I omit that R n. Okay. So, that is L P means L P R n. Every time. Okay. So, like we did in the estimate of WTF. So, same thing we will do now. So, WTF of x minus Fx. So, this is nothing but integral k T x minus y f of y minus f of x. This is dy. Okay. So, just each time we are using those properties of the heat kernel k T, that integral is 1. Okay. So, all the time we are using that. Okay. So, similarly what we did in the previous thing. So, now we take absolute value and raise to the power p. So, this get W T F x minus F x to the power p. So, when p is equal to 1, so there is no trouble at all, but when p is bigger than 1, you again use Hölder's inequality to get this k T. Okay, so, this is dy. Okay. So, again just now integrate with respect to x and interchange the order of integration using Fubini. So, you get that. So, this implies W T F minus F. So, let me write that L P to the power p. So, let us keep that for the moment. Okay. So, this is less than or equal to. So, let me just write once. So, this is integral dx integral So, I am going to interchange the integral and also make this change of variable in the integration. So, especially with respect to y. Okay. So, this put x minus y is equal to z into 4. Okay. This 4t is coming from this k T. Okay. If you do that, So, this is less than or equal to, let me write that, pi to the, so some cancellations are taking place. So, this in particular we get rid of this t factor here. So, let me just k t z d z and f of x minus 4 t root z minus f of x p dx. Okay, so just so normally the in textbooks you see, in many textbooks they are correct in some way, but not fully correct. So, now you use the continuity in the norm of L p. So, as t tends to 0, this goes to 0. Okay. So, there is some catch here. So, let me just make that clear. So, this you okay, let me just why you have to do little more. So, from the continuity in the norm, we obtain. Okay. So, let me just this given epsilon positive, there exists delta positive such that for all mod h less than delta, we have norm of f plus h minus f. You take this in the LP norm is less than epsilon. So, this is the statement that there is continuity in the norm. Okay. So, in our case, so just taking t small will not fully justify, because there is a z hanging over and z is not in a bounded set, z is in whole of R n. Okay. So, just remember these are integrals on R n. Okay. So, this smallness of t is not uniform. Okay. So, we have to do little more. So, for that what we do is, so we write this right hand integral as I1 plus I2. Okay. So, we also learn how to do some rigorous mathematics. Okay. So, where okay. So, I1 is so they leave that constant pi. So, that is so this is mod z bigger than R, same thing whatever k t z d z, and we have this integral, another integral there. Okay. So, this R is a positive number, etc. And I2 is mod z less than or equal to R, same thing. Okay. In this the first integral, so this I1 is less than or equal to, so let me just write that constant norm f p integral mod z bigger than R k t z d z. So, the inner integral I estimate by norm p, and since k t is an integral function, this can be made this can be made as small as we please by choosing R large. R very large. Okay. And once you make R, you fix that R for which we can make this integral as small as we please, and then you apply the same thing here. So, now this mod z is bounded. So, I can use this continuity in the norm. Now, z is bounded. Okay. So, I can use take small t in here we can take t small to make I 2 small using continuity. Okay. So, these are subtle issues in analysis, we have to learn that. Okay. That proves the strong continuity of the semi group we want to. So, this finally we got this. So, thus W t is a strongly continuous semi group. In LP and for that range of P. Okay. So, next we proceed to find the generator of W t. Of W t, and in the definition of this semi group, nowhere do we see the Laplacian. Of course, Laplacian we see only through the heat equation. Okay. So, you want to guess that it is going to be Laplacian is not immediately clear, but we have that background of heat equation, and that is how we proceed. Okay. So, that is the next proposition. Okay. So, the generator, and you will see some surprises, generator of W t is the Laplacian. So, more importantly, so we have studied even in the abstract theory. So, we have to describe the domain of that generator, right. So, with domain, so let me write that d Laplacian P. Okay. So, this is the set of all LP such that also in LP. Okay. So, this is in the sense of distributions. So, let me just write that once, sense of So, you have to keep on recalling these things. Okay. So, this you have to get used to that. So, this means what? So, f of Laplacian phi is equal to, after this happens then only. So, there exists a an LP function. First you call it G, okay. So, and this holds for all phi in DRn, okay. The distributional Laplacian, if you want to call, and that you demand it to be again an LP function, okay. So, this keep on recalling these things from the previous part of this course. So, what we have to show in this proposition, so you learn many things here. So, first of all, for f in this okay, for this thing, that any f in this d delta p, Laplacian p is in the domain of the generator, and generator we do not know, we have to show that is delta, and conversely if something is in the domain of the generator, then we have to show that element also belongs to this subspace, and AF is given by delta f. Okay, that we have to show. Okay, so proof. So let A be the generator of Wt. From the abstract theory, of course, we know that the domain of A is dense in LP and A is a closed operator, all those things we know. Okay. So, now in this case we have to show that the domain of A is precisely that set given by d delta p, and AF equal to Laplacian f for those f. Okay. So, we have two things to show. Okay. So, some surprises about or no, I should not say surprises, but certain things are not clear. Okay. Let me just comment on those things. So, d Laplacian 2. Okay. So, this is f in L2 and Laplacian f in L2. So, this is in Rn. Okay. So, just remember that. So, using Fourier transform, so this equality, so this you can show precisely it is H2 of Rn. Okay. So, this is for p equal to 2. Okay. But such a thing, such a statement is not true in a bounded domain. So, if you replace Rn by a bounded domain, so we may have functions in L2 such that the weak Laplacian is also in L2, but the first derivatives fail to be in L2. Okay. So, this is the first one, and question. Now, we lose this power of Fourier transform. So, this question, let me say W2p. Okay. So, that is the question, okay, whether it is equal to or. I will make more comments as we go further. Okay. So, now proof in. So, let us begin with something simple. So, for phi in C infinity C Rn, we have this. So, from the classical theory we have W t phi minus phi divided by t minus Laplacian phi, in fact not just p, any p tends to 0 as t tends to 0. Okay, so here it is important that, okay. So this how do you prove? How do you prove that quickly? So this is for all p prime. Okay, because of this compact support assumption. Okay, so proof of this. This requires a quick proof. So put V of x t is equal to W t of phi of x. So from the classical theory we know that then V of t is equal to Laplacian V, and so let me just V of x t converges to phi of x uniformly, because that is compact support, uniformly in x as t tends to 0. And again for t positive these are all smooth functions. So that further implies the Laplacian V, so Laplacian with respect to x variables, also converges uniformly to Laplacian. Same thing. Okay, so we are using heat equation. You see that this function given by the Fourier Poisson formula is indeed satisfy the wave equation. Okay. So next, so we have V of x t minus V of x 0. So I get just 0 to t, maybe I will just tau V of x tau d tau, but they satisfy the wave equation. So you just get 0 to t Laplacian as x tau d tau, and now you divide by t, divide by t, and let t tends to 0. And you can use any norm you like, any norm you like. So you just write this W t phi minus phi by t minus Laplacian phi, any norm you like. So this is less than or equal to 1 by t 0 to t Laplacian V x tau minus Laplacian phi x d tau, and that tends to 0, because from this in any norm you like. So that is the first step. So for at least for smooth functions we know that. Okay. So thus the class of smooth functions is in the domain of the generator, and A phi is equal to Laplacian phi for phi n. That is the first step. So, in particular dA is dense, dA is dense in okay. So, now we take the first part. So, now take f in d delta p. Okay. So, this is set of all f in LP whose distributional Laplacian is also in LP. So, we would like to show that f is in the domain of the generator and AF is equal to Laplacian f. Okay. Okay. No, just no, first here I have written, let me go as I have written it. So, just okay. First you take f in t. So, then there exists G in LP. This is by the definition of the domain of the generator, such that this W T f minus f by T minus G in P LP naught tends to 0 as T tends to 0. So, this is the definition of the generator. Okay. So, now for again phi smooth, so test function. So, we have, so this is some computation. So, this is Rn integration Gx phi x. Okay. So, I will leave it as some exercises. So, the interchange of limits and integral. So, this can be done. So, T inverse W T f minus f x phi x dx. Okay. And this is an integral operator. So, you can just pass this W T onto f. So, you just write down, you see that. So, this is f of x W T phi of x minus x phi x by t dx. Okay. Just these are integral operators. So, you just change to that, that is fine. And now we have seen that this, just now we saw that. So, this converges to Laplacian, in fact uniformly. So, this gives us f of x. So, again this is Rn, and that shows that f is in so this G is nothing but AF. F is in this Laplacian P and G is Laplacian F. But G is also AF. So, that is, so this is one way. So, if we start with an element in dA, we conclude that that is in this space D Laplacian P and A of f is equal to del f. Okay, so this is what we want. So conversely, so then we will suppose f is in D Laplacian P and we need to show f is in the domain of the generator and AF is Laplacian. Okay. Okay, so put G equal to Laplacian f. So this is in the weak sense and by assumption that is in LP. Okay. So for again some computation. So for t bigger than 0, you consider this 0 to t w tau g d tau. Okay. So this is a function actually. Okay. So we are suppressing that. Okay. We are not suppressing, so just not written. Okay. Of x, let me write that, phi of x d tau. Okay, so this again phi is in C infinity. Okay. So this, remember this G is Laplacian f. So okay, then I want to integrate this with respect to x. There are two things. Okay. So you interchange the integral. So just see that these are all justified. So let me write that w tau g of x phi x dx and then d tau. As you did in the previous case, so you transform this w tau to phi. Okay, just let me write that. So verify these things. Let me write that. So fx. So I am skipping one step here because G is Laplacian of f and Laplacian also I am taking to phi. Okay, so you do it twice. So w tau Laplacian phi of x dx and then d tau. Okay. And again you see phi is smooth. Okay, and this is the solution of the heat equation w tau phi. So this is precisely is equal to del tau phi. Okay, so very subtle things. So again you interchange the integral fx dx, and now if I integrate this derivative with respect to t. Okay, so I get w delta w tau. So, again we are using that it satisfies the heat equation. So, you do it carefully. So, this is nothing but, so let me write that del tau W tau phi, because it satisfies the heat equation. And now if you do in this T integration or tau integration, so you get W T phi, and at 0 it is identity, so it is just x dx. Okay. Next, okay, and now again you transform this W t to F. Very nice computation, so you should do that. Okay, so let me one more line, I just say that. Okay. So, this is true for all phi in C infinity. So, we conclude that W T F minus F is equal to 0 to T W tau G d tau. Okay, because that relation holds for all phi which are C infinity with compact support. And now divide by T, and let T tends to 0. So, it shows that this limit exists. So, conclude that AF is precisely G, W0 G. So, this is G. Okay. So, let me stop here, and I will continue with little more remarks on this thing, and then we will discuss some more. Actually the converse problem, I will discuss that. Thank you.